Today we're going to talk about similarity in right triangles, and this section really is a bridge between Chapter 7, where we talked about similarity in all triangles, and Chapter 8, where we will specifically be focusing on right triangles. So the first thing I want to talk about is a geometric mean. And you see here that we have a proportion with A is to B as C is to D. And the means of this proportion are these two variables that are across from each other. And when you set up your proportion like this, A is to B as C is to D, A and D are the extremes because they're outside, and B and C, they're kind of on the inside of this, so they are called the extremes. And you see that when it's written as a normal proportion. So one way that we can define a geometric mean is that it's going to be the square root of their product. So let's take a look. If we see you have A is to X as X is to B, we see that our mean is X. And if we cross multiply here, we'd get X squared equals A times B. And if we were just going to solve this, we would get X equals the square root of A times B. So this right here is the definition of a geometric mean. Again, it's going to be the positive square root of the product. So let's take a look. They ask us to find the geometric mean of 9 and 4. And by definition, it's just going to be the positive square root of the product of the two numbers. So the positive square root of 9 times 4. And we know that 9 times 4 is 36. So when we take the square root of 36, the geometric mean, or X, is just going to be 6. So that's going to be our geometric mean. So why don't you all try these next two, and I'm going to pause the video and you can come back and check your answers. You'll notice on these that instead of multiplying 5 and 45 or 12 and 15 and getting these really big numbers, I actually just broke these down into factors so that I could easily pull out my perfect squares to simplify. Okay, so now what I want you to do, I want you to look at this next one. We are going to do a proof, and I want you to look at this figure and see if you can prove any two triangles that are similar. And each group may come up with a different set of two triangles that are similar. That is totally fine. You'll notice here that there are three triangles. So see if you can come up at least with one pair of similar triangles and come back and check. There are several different ways to go about these proofs, and I did a really long proof to basically prove that the blue triangle is similar to the overall green triangle, the yellow triangle is similar to the overall green triangle, and the blue and yellow triangles are similar to each other. And you can take a look at that and compare that to what's in the content library. So I do want to take a look at this a little bit closer. So if we look at our overall right triangle, again, you notice that an altitude is drawn to the hypotenuse of that right triangle. And I pulled out each individual triangle here. So we have our overall triangle here, ABD. We have the triangle that's on the left, and then the triangle that's on the right. And like I said, there's a theorem here that the two triangles that are formed by that altitude are similar to the original triangle and then to each other. So if we name this first triangle, triangle ABD, so we're going to call that ABD, and I would say and recommend this, I'm going to mark my angles B and D. And I can also mark those on all my other figures just to be consistent. That will help us know how to name the other triangles. You'll notice that we started with our right angle. So if we look at this middle triangle, we want to start with the vertex at our right angle, which is C. And from here, in this one, we went from A to B that had one marking, and then we ended up with the angle with two markings. Now, if we look at this triangle right here, we don't have an angle with one marking, but we do want to end with the angle that has two markings. So this one is going to be triangle CAD. And then the last triangle, we're going to start with our right angle, which is angle C. And again, we're trying to go from the right angle to one marking. So here we're going to go C to B, and then the last vertex is going to be A. So now what I want to do is talk about what kind of proportions that we can set up with these similar triangles. So I'm going to highlight some of these triangles to help you see what we're doing. You see over here, this left triangle I'm going to highlight with yellow, and this is going to be the ratio that we have right here on the left. And then I'm going to do the triangle on the right side. I'm going to highlight that, and it's going to be the proportion that we do on the right. Now, in this particular instance, what we are going to do is we are going to actually compare by looking at this figure. We're going to compare the short leg to the long leg. And let's take a look. So if we look in the yellow triangle, again, we're going by looks here. Our short leg is going to be A, and our long leg here is going to be E. And if you look at the green triangle, you'll notice that E is actually the short leg in the green triangle, and B is the long leg. And so you notice what sets up is that E is the geometric mean, right? If we cross multiplied, we'd get E squared equals A times B. And so E is going to be the square root of A times B, which is the definition of our geometric mean. And E in this case is the altitude. And so what this generally is going to tell us is that the altitude is going to be the square root of one part of the hypotenuse. So you can just call this a hypotenuse part, which what we just did was A times the other hypotenuse part, which in this particular example was B. You see how the altitude cuts the hypotenuse into two pieces. So the altitude is going to be the geometric mean between one part of the hypotenuse times the other part of the hypotenuse. And here is our corollary. And it says when an altitude is drawn to the hypotenuse of a right triangle, the length of the altitude is going to be the geometric mean between the segments of the hypotenuse. So it's a lot of words, but let's take a look at an example here. So they give us an overall right triangle, and they tell us here this altitude. We see that it does form a right angle with the hypotenuse. So we've got to solve for x. So again, we know that x is going to be the geometric mean. So we could, because it's the altitude, we can go in and put it in the mean spots. And then it's the geometric mean between the two segments of the hypotenuse. So one of the segments is 4 and the other is 12. And then we've got something pretty easy to solve. We can cross multiply and get x squared equals 4 times 12. And so x is going to be the square root of 4 times 12. And you could multiply this out, but ultimately what you want to do is simplify this. And I just usually, I'm going to break down 12 into 4 times 3. And the square root of 4 times 4 is just going to give you 4, and then we have 4 times the square root of 3. So if you'll pause your video and work on these next two and then come back, one thing I do want to note in the second example here, this is an altitude that has a length of 9. I just forgot the right angle. So work on this and come back and check your work with me. So the first one you should have gotten 3 radical 5. You'll notice how I broke this down instead of multiplying out 3 times 5. And for the second one, I got x equals 27. Now, because of properties of proportion, it doesn't really matter if you put x up here and 3 down in the denominator right here, because when you cross multiply, you still should get 81 equals 3x. Okay, so the first thing that we have found so far is that the altitude is the geometric mean, I'm going to just abbreviate that, GM, between the parts of the hypotenuse. Okay, so the altitude is the geometric mean between the parts of the hypotenuse. Okay, so that's one proportion that we know, and we're going to learn a second one right now. So here, we're going to take a look at our figure, and this time what we're going to do is we're going to create a proportion comparing the short leg of the triangle to the overall hypotenuse, and one using the long leg to the hypotenuse. So let's take a look. So in this first one, we're going to actually compare the short leg, the short leg to the hypotenuse. And this first ratio, we're going to look at the left triangle on the left side, and then the next ratio, we're going to look at the whole triangle. So I'll highlight these just so you have a better feel for what I'm talking about. So here, when we're looking at the left triangle, we're going to look at this triangle right here that I'm highlighting. And then when we look at the whole triangle, again, we're going to be looking at this whole thing right here. I'm just going to highlight the outline. Okay, so if we look at this left green triangle, the short leg in this particular case we see is marked as B. And the hypotenuse in this green right triangle is just going to be a length of C. Now, if we look at the overall triangle here, the short leg ends up being C, and the hypotenuse ends up being the entire hypotenuse, which we see the entire hypotenuse is just going to be A plus B. So you can see here, if you cross multiplied, you'd get C squared equals B times A plus B. Now, before we generalize this, I want to look at the other situation. So in the other situation, what we're going to do is that we are going to look and compare the right side triangle and compare it to the whole triangle. And in this case, we're going to compare the long leg to the hypotenuse. And we know that our overall triangle is yellow, so we'll keep that consistent. And then I'm just going to color the right triangle, the right side triangle, in blue. So I'll color this in blue right here so that stays, so you can see where I'm pointing. Okay, so if we look, again, we're going to compare the long leg. So if we look in this blue triangle, the long leg here is A. And the hypotenuse in that right triangle is going to be D. Now, if I look at the overall triangle here, my long leg is D, and my hypotenuse, just like we saw before, is A plus B. So if I cross multiply here, I get D squared equals A times A plus B. So what we have just proven is that you notice in the overall triangle, both C and D are legs in that right triangle. So what we've just proven is that the leg, and I'll actually, instead of writing it out, we'll just use the words down here. So each leg in that overall triangle is going to be the geometric mean between the entire hypotenuse, which we saw that to be A plus B, and the part of the hypotenuse it touches. So if you look, C is the geometric mean between B, you see this, B is the part of the hypotenuse it touches, and the entire hypotenuse. Whereas D, which is the other leg, is the geometric mean between the part of the hypotenuse it touches and the entire hypotenuse. So let's take a look as an example together. So here we've got our altitude drawn, we've got our two pieces of the hypotenuse, and we know that the entire hypotenuse here is just going to be 20. So we know our leg is going to be our geometric mean, so I'm going to put that value there, that my x is in those two corners, and it's going to be the geometric mean between the part of the hypotenuse it touches, which is right there at 5, and the entire hypotenuse, which is 20. And when we cross multiply, we get x squared equals 5 times 20, which is 100, and when we solve that, we get x equals 10. This next one, we see that we're trying to find the, we're given a leg, and we're not actually given the length here. So we can actually call that x, which would mean the entire hypotenuse would be x plus 5. So why don't you set up this proportion and come back and check your answer. So when you set up your proportion and cross multiply, you get a quadratic that you have to set to one side equal to 0 and factor. We can't have a length equal to 9, so that is extraneous. So just remember the leg is the geometric mean between the hypotenuse